Imagine building a computer so unusual that, after seeing what it can do, some people begin asking whether our understanding of reality itself is incomplete. That question resurfaced in December 2024 when Google introduced *Willow*, a new quantum processor designed to push the boundaries of quantum computing. The announcement quickly attracted global attention after Google reported that Willow completed a specialized benchmark in just a few minutes, a task the company estimated would be unimaginably difficult for today's fastest classical supercomputers to reproduce. The achievement wasn't important because it solved a practical everyday problem. It was important because it demonstrated how differently a quantum computer behaves from every machine humanity has built before. At first glance, Willow looks surprisingly ordinary. It isn't a giant futuristic device filled with spinning machinery or glowing reactors. Hidden inside a carefully engineered cryogenic system sits a processor containing more than 100 superconducting qubits, operating at temperatures only a tiny fraction of a degree above absolute zero. Those extreme conditions are essential. Unlike the transistors inside a conventional computer, quantum bits, or qubits, are incredibly sensitive. Heat, vibration, stray electromagnetic signals, or even tiny disturbances from the surrounding environment can destroy the fragile quantum states needed for computation. Keeping those states alive long enough to perform useful calculations has been one of the greatest engineering challenges in quantum computing. Yet Willow managed to demonstrate something remarkable. Using a benchmark known as *random circuit sampling*, the processor completed its calculation in under 5 minutes. Google estimated that reproducing the same benchmark with today's leading classical methods would require an amount of computation so enormous that it becomes almost impossible to picture. Whether future algorithms narrow that gap or not, the result highlighted something fundamental. Quantum computers are not simply faster versions of ordinary computers. They process information in an entirely different way. A traditional computer stores information as bits. Every bit has a definite value, either 0 or 1, and calculations proceed through long sequences of logical operations performed one after another. Quantum computers operate according to the laws of quantum mechanics. Their qubits can exist in combinations of states known as superpositions. When multiple qubits become entangled, the information stored across the system grows extraordinarily complex, allowing the processor to represent relationships that quickly become impossible for classical intuition to visualize. The true power of quantum computing does not come from trying every answer one by one. Instead, carefully designed quantum operations cause different possibilities to interfere with one another. Some possibilities reinforce the correct solution while others cancel out, increasing the probability that the desired answer appears when the system is finally measured. That process is one of the most fascinating aspects of quantum mechanics. It also raises a deeper philosophical question. What is actually happening while the quantum calculation unfolds? Physicists agree on how to predict the results of quantum experiments with extraordinary accuracy. What remains debated is what those mathematical equations mean about reality itself. One famous explanation is the many worlds interpretation first proposed by Hugh Everett in the 1950s. According to this interpretation, quantum possibilities never truly collapse into a single outcome. Instead, every possible result continues to exist in separate branches of reality, with each branch evolving independently after a measurement. This idea has been explored by several influential physicists, including David Deutsch, who has argued that quantum computation is naturally described within this framework. It's important to understand, however, that many worlds is only one interpretation of quantum mechanics. Other interpretations explain the same experimental results without requiring parallel universes. At present, no experiment, including Google's Willow demonstration, has confirmed which interpretation, if any, reflects the true nature of reality. Still, quantum computers make these philosophical questions feel more tangible than ever before. A classical computer resembles someone solving a maze by exploring one route after another. A quantum computer instead manipulates probability amplitudes so that countless possibilities interact through quantum interference before the final measurement occurs. Nothing travels faster than light. No hidden portal opens. Yet the mathematics guiding the computation is unlike anything encountered in classical information processing. That difference is precisely why Willow attracted so much attention. The processor wasn't designed to prove the existence of parallel universes. It demonstrated that carefully controlled quantum systems can perform tasks whose behavior simply cannot be described using the same intuition that explains ordinary computers. Perhaps Willow's most significant achievement wasn't even the benchmark itself. It was the progress Google reported in *quantum error correction.